This video is on section 4.3 notes, the rules of logarithms. So first, we have the inverse rules, which have not been written out like this, but we've already talked about. So for the first example, it says e to the ln of x squared, and another way to write that is e to the log base e of x squared. And if you have an exponential expression where the base of the exponent and the base of the log match each other, then they're inverse operations and they cancel each other out. So e and log base e cancel, and you're left with just x squared. And so back here you can say e and ln cancel, and you're left with just x squared. Same thing over here for this logarithmic expression. Bases for exponential expressions and logs, they're inverses of each other. So if this is log base 7 and then an exponential expression with a base of 7, those cancel each other out because they're inverses of each other, and we end up with 2x minus 1. For the next rule for logarithms, we have the product rule, and if we still think of logarithms as the inverse of exponential functions, then one way you can kind of remember this rule is to think about your exponential rules. So if we had like x squared times x to the 7th, to figure that out, we would take the exponents, we would add them together, and we would get x to the 9th. So we know that when we see a multiplication problem, it really means that you're adding. For logarithms, it's kind of like the inverse of that. When you see that two logarithms are being added, it really means that they're being multiplied together, or that what you're taking the log of is being multiplied together. So this is log base 3 of 6x. This one, we have 3 logs we're adding together, so we're going to think of multiplying the 3 things that we're taking the log of. So ln, or log base e, is of 3x squared y. And in both of these cases, you can have the parentheses there, or you can write it as, this one could be log base 3 of 6x, this one could be ln of 3x squared y. Technically, you don't need the parentheses because you're doing the log of this group, you're doing the log of this group, but having the parentheses there isn't a bad idea. All right, for the next one, quotient rule for logarithms is going to remind us of our exponential rules. So if we had x to the 11th power and we divided by x to the 3rd power, we would just subtract our exponents. We would say this is x to the 8th power. So when we see that we have 2 logarithms being subtracted, that really means that we're dividing what is inside the logarithm. So this would be the log of 24 divided by 4, which is log of 6. This one over here would be ln of x to the 6th over x to the 2nd, which is ln of x to the 4th. And again, same thing I said above, you can put this in parentheses if it makes you more comfortable to think of multiple things happening at once. But technically, when you have a fraction like that, it is considered to be one group, and taking the log of one group makes sense. The only time you really need parentheses around what you're logging is if it has a plus or a minus in the middle of multiple terms. And then you would have to put that group in a parentheses. Otherwise, if you can see that the group is already kind of complete on its own, then you technically don't need the parentheses, and it really comes down to just personal preference. All right, the next one is the power rule for logarithms, and this might remind you of the exponential rule where you're raising an exponent to an exponent, but it might not. This one is a little bit more of a stretch. So if we think of x to the 3rd to the 4th, we would multiply the exponents together, x to the 12th. And here the power rule says that if you have log with a certain base of something to an exponent, you can take the exponent and move it to the front as a multiplier. So you're still multiplying. So if that helps you to remember, then use it. If it doesn't help you to remember, then don't use it. But for these, the instructions tell us to rewrite all of these in terms of just log of 3. And so this is log of 3 to the 8th power. So the 8th power would just move to the front, and it would be 8 times log of 3. And this makes sense if you think of that previous rule we learned about, the product rule, because the product rule would tell us that we have log of 3 times 3 times 3 times 3 times 3, that we have that 8 times. And then the product rule tells us that we could write this out as log 3 plus log 3 plus log 3 plus log 3, because when these are being multiplied, it's really like you have separate logs that are being added. And if it was 3 to the 8th power, that means that there were 8 of them. So 8 log 3s. All right, with this one, I have to rewrite this so that 3 has an exponent instead of a radical. So this would be 3 to the 1/2. And then I'll go ahead and take that exponent and move it to the front. So I have 1/2 log 3. For this one, again, I'm going to rewrite this so that it is log 3 with an exponent. So this would be log 3 to the -1 power. And then the -1 can move to the front. So that'd be -1 times log 3, or just negative log 3. And this is one that I think is easy to not recognize. And I've seen shown up a bit when I was teaching high school. I noticed problems like this particular property of logs would show up in multiple choice answers on AP problems, where students would have like this when they did it by hand, but then this was the multiple choice answer that showed up. So kind of interesting, something to watch out for. I'm not sure if my math lab does things like that or not, but this would be really easy to miss. Okay. Let's go ahead and look at some more problems. So here's all of the formulas kind of summarized for you. And so now we're going to get a little bit more creative with this. It says to rewrite each expression in terms of log 2 and log 3. So if we're trying to create log 6, I have to think about what I can do with 2 and 3 to get to 6. And most of us would probably be like, yeah, I should rewrite this as 2 times 3. 2 times 3 is 6. So if I need to have log of 2 times 3 to get that 6, then this would be log 2 plus log 3. Technically, this is right. The reason this was not my final answer is because the instructions told me to write it in terms of log 2 and log 3. So I couldn't write log 2 times 3 because that's not following the instructions. Okay, the next one says log 16 over log 3. And so for this one, I can see, clearly that's a division problem. And so I'm going to think of this as log 2 with something over 3. I can see the 3 on bottom. That's pretty easy to recognize. 2 is actually, if you relate the 2 to the 16, if you look back at your previous notes, then you can see that 16 is 2 to the 4th, or you might know that off the top of your head. But we can rewrite that top portion as 2 to the 4th power. And so I know this is going to be a subtraction problem because this is division. So log of 2 to the 4th minus log 3. And then I have to write log 2, not log 2 to the 4th. And so I'm going to take this 4, move it to the front. So 4 log 2s minus log 3. And if I wanted to be really specific about it, I could say that the top was really 2 times 2 times 2 times 2, 4 times. And so that it was log 2 plus log 2 plus log 2 plus log 2, and then minus log 3. if I really wanted to do that, but I think this is fine. And then the last one, this example I took from the book, but it feels a little redundant at this point. Like we said on the previous page, you can write this as log 3 to the negative 1, and then take the negative 1 and put it in the front. Okay. All right, for the next example, it says to rewrite each expression using sums and or differences of multiples of logarithms. And that, I've never seen a textbook phrase questions like this that way. What they're saying is to take this expression and to use the rules of logarithms to expand it out. That's the more common phrasing that I've seen in the past. So that's what this note is. Other textbooks might call this expanding the logarithmic expression, and in my experience that is the more common phrasing. So when they write this, they're really saying expand the logarithmic expression, which means that when you see multiplication, you're going to write it out as addition, the addition of two different logs. When you see division, you're going to write it out as the subtraction of two different logs. So to figure out how many times you have to write the word log, or in this case ln, you just look at how many like factors kind of you have multiplied together and then just count them. So I would say 3 is 1, x squared I'll count as 1 because it's the same variable. So 1, 2, 3, 4. I'm going to write the word log or ln 4 times when I expand this out. Since these are being multiplied together, I'm going to have a plus between them, and then we have a division problem, so we're going to have a subtraction sign right there. So I'm going to say for the numerator, I have ln 3 plus ln x squared. And then the rest of it is division, so I'll say minus ln y minus ln z. And then I can go through and say the x squared has the exponent, so I'm going to take that and move it to the front. So I have ln 3 plus 2 ln x minus ln y minus ln z. So this is a great answer right here. Probably the most common way I would see the answer to be written. Some people look at this and they can say like, yep, I can see that multiplication on the top, ln 3 plus 2 ln x. And then they say, yep, this is a division problem, so I'm going to do subtraction. And then some people look at the bottom and say ln, the y and the z are being multiplied together. So I'm going to write ln y plus ln z. And I put it in parentheses with a minus in front of it, and the minus in front of it shows that this set of parentheses, these things that are being multiplied are multiplied together, but on the bottom. So this is an acceptable answer, but I'd say this is probably more common. And algebraically, you can see how these are related. You know, this is like, well, this is, you just kind of looked at what you had, but here you can distribute the negative and end up getting the same thing. So it's up to you in a testing situation. I would honestly take both of them, but I'm not sure if my math lab is going to be picky or not. So that's something to keep in mind. For the next one, I can see this right up here. This is a group. These are not two different factors. This is one factor that's been squared. So I see one thing up here and one thing down there. And so we're going to write the word log 2 times, and it's a division problem, so it's going to be subtraction. So log base 3 of x minus 1 squared minus log base 3 of z to the 3 halves. And here you'll notice I had parentheses with my log, and this is the only example so far in these notes. I'm looking back. Yeah, this is the only example so far in these notes where the log had to have parentheses in the expression to be accurate. All the other times when I put the parentheses here, 2 times 3 here, 6x here. When I put the parentheses here, it was just for my personal preference. It didn't matter. It's just because it made me feel more comfortable when I was looking at it. But for this expression right here, if you don't put the parentheses, if you put log base 3 and have x minus 1, you're actually writing it incorrectly. So that's something to be aware of. All right, so I'm going to take my exponent. I'm going to move it to the front. take my exponent, move it to the front. So I have 2 log base 3 of x minus 1 minus 3/2 log base 3 of z. So this would be the expanded form. If you really wanted to be tricky about it, you could say log base 3 of x minus 1 plus log base 3 of x minus 1, and then minus this. Since this is squared, it's happening twice. All right, in the next example, it says rewrite each expression as a single logarithm. That's pretty common phrasing. Other textbooks might call this condensing the logarithmic expression. And that just means to take the expression that has multiple logs in it and use your logarithmic rules or your properties of logarithms and rewrite it so there's only one. So single expression or condensing, the phrasing here is not too bad. And so how I always think of this is anything, I always do like my log and think of it in terms of like a fraction. Anything that's being added is going to end up in the numerator, and anything that's being subtracted is going to end up in the denominator. And before I get started, it's kind of nice to figure out my exponents. So the 3 in the front is actually x to the 3rd. Okay, so these are being multiplied, so they're going to be in the top. So I have x minus 1 times 3. And then in the bottom, I have x to the 3rd. And I technically don't need parentheses around this because the fraction makes it a group. So this is ln of, you could say 3 times x minus 1, or you could distribute and say 3x minus 3. But this is ln of this fraction, this group. And if it makes you uncomfortable to look at it like that, go ahead and put it in parentheses. All right, with this one, I'm going to take these numbers and make them the exponents. And then since this is a subtraction problem, I know that I'm definitely dealing with a fraction. So the top is y to the 1/2, the bottom is z to the 1/3. Depending on what they expected from the answer, you could leave it like this, but both of those exponents are radicals. So this would be square root y, cube root z. And then again, we technically don't need parentheses, but you're welcome to put them if you want. All right. And then the last page, this is moving on to something a little bit differently. This is called the change of base formula. So we have a few different ways we could solve this problem. You know, we could change the bases and make them the same. So you're probably already looking at this going, well, 9 is 3 squared. So I know that x equals 2. But it says to solve this equation by taking the natural log, that's ln, of each side of the equation. So I'm just going to show you how that would work. So if I did ln of 3 to the x equals ln of 9, and notice I'm writing the log on the left side because whenever you use a log, you're doing the log of something. Then here I'd have to use my log rules or my properties of logarithms to take the exponent and move it to the front because that's how log rules work. And then if I wanted to get the x alone, I could just take the ln 3 and divide it over to the other side. And if I look at this problem, ln 9 divided by ln 3 is 2, which is what we expected. I would never do this problem this way because I would do exactly what you probably did and say, well, you know, 9 is 3 squared, so there's my answer. But I'm using this problem to demonstrate the change of base formula. So I'm going to show you this exact same problem but solved a different way. So if we have 3 to the x equals 9, and we wanted to solve it using logarithms, then we could undo the base of 3 by log base 3, doing log base 3 on each side. This is solving using inverse operations rather than solving by changing the base of the problem. So log base 3 of a base of 3, those cancel out, and I get x equals log base 3 of 9. And if you look, math up, log base 3 of 9 is also 2. So what that tells us is that ln 9 over ln 3 is the same as log base 3 of 9. And this is what the change of base formula is all about, is that if you don't want to type in a base of 3, or back in the day, before you had the ability to type the math button and go up and use a log and change the base, back in the day when we had to use only the log button or only the ln button, this is how you could type this in on your calculator. You could type ln 9 divided by ln 3, like we did, or you could type log 9 divided by log 3, and it would give you the same answer. So that's what the change of base formula is all about. So now we're going to use the change of base formula to evaluate each of these without using the function on our calculator where we hit the math button, go up, and actually type it in. We're not going to do that. We're going to use the change of base formula. So this one is ln 7 divided by ln 3. So ln 7 divided by ln 3, 1.771. Log base 1.03 of 5 would be ln 5 over ln 1.03. $54.449. Log base 5.44 of 2.3 would be ln 2.3 over ln 5.44. And all of these we could have calculated the normal way. So we could have said math up, log base 3 of 7, and we would have gotten 1.771. We could have said math up, log base 1.03 of 5, and we get the same decimal. But this is just another way of typing it. And it's nice because if you don't have the updated version of this calculator, if you have an older version of this calculator, now you can actually plug in your logs and get the right answer. Okay, so this last problem is more of an application problem, and it says if $2,500 is invested at 6% compounded daily, and when it says compounded daily, that tells us we're using A is P 1 plus R over N to the NT. The other formula would use the wording compounded continuously. That was the PERT formula. So this one, when it says daily, we know we're using this one. Then how long to the nearest day would it take for the investment to double in value? And it says use the change of base formula to solve the problem. So that just means we're going to use the change of base formula when we plug it into our calculator. So we have $2,500 is invested, 6%, compounded daily. Then how long would it take for the investment to double in value? So if we're starting at $2,500 and we want to double that, then we want to end with 5,000. Okay. So we're going to say 5,000 equals 2,500, 1 plus 0.06 over 365 times 365 to the t. Well, not to the t, but 365t. Okay, so I'm going to get as close to I can as having the t be alone. The first thing I'm going to do is divide by the 2,500. And since this was doubling the account, when I divide those, I get 2. there's a pretty good chance this is going to be a decimal that is not very nice. I'm just going to see what it is. We don't want to round, we don't want to round in the middle of the problem. So unfortunately, I'm not going to be able to use this decimal because I can't round yet. So, I'm just going to keep writing this. Okay, so to solve this problem, I need to get rid of this, the base of the exponent. So I'm going to say log base 1 plus 0.06 over 365 on the right side, and log base 1 plus 0.06 over 365 on the right side. So this is my base of my logarithm because I have to undo the base of the exponent, and it's just kind of a messy number. So if you want to write down like a rounded version of this to show your work, that's fine. But don't use a rounded number because it could impact your answer. So log with that base and the base cancel out, and I end up getting that log base 1 plus 0.06 over 365 of 2 is 365t. And then to solve for t, I'm just going to divide the whole thing by 365. Okay, so to type this in my calculator, I'm going to do the change of base. So I'm going to do ln of 2 divided by ln of this. 1 plus 0.06 divided by 365. So that's this. And I can show you again, I can actually type it in as a log. So log base 1 plus 0.06 divided by 365 of 2. Same answer, okay? I'm taking that divided by 365. 11.553. T is 11.553. And it said, how long to the nearest day? So I'm going to subtract 11. This is the number of days. It's 11 years and however many days. And I'm going to take that and multiply it by 365. 202 days. So 11 years and 202 days because there's 365 days in a year. So we have 11 years, 202 days. And I'm going to write a little note to myself. I did 0.553 times 365 is approximately 202 because it said round to the nearest day. So if they only asked how many years, then you could say 11.553 years. But since they asked for to the nearest day, 11 years, 202 days.